Okay, and now you have in front of you where we stopped last time. Just as a brief review, things that you have seen, but I would like to connect with last Monday's lecture and remind you that now for uh, excitations which are monochromatic, meaning, or who are harmonic, we use either monochromatic or harmonic for excitations which only involve one frequency. And you will see this here. All right, so that's a harmonic or a monochromatic excitation. Harmonic comes from music, monochromatic comes from up. All right, just so historically, you know why we call them like this. And we assume in this particular case that V of t, which is a voltage in time domain, is expressed as a cosine function multiplied with a real number, positive real number. And then we remember from complex number that a e to the j omega t, we here remember that e to the j omega t can be written as a cosine of omega t plus j sine of omega t. And then as a result, we can write v of t to be equal to the real part of this complex number. This complex number is a function of frequency and time, but in a different way. And then from this complex number, we assume that always this is going to have the j omega t dependence for any harmonic or monochromatic excitation, and we keep only the amplitude here, and we call this the phasor. Also, we can demonstrate that by doing that, we can then take a circuit like this, which is in the time domain, and which is characterized by these equations, if you remember from the time domain, from the circuit work that you've done in 214. You will remember, let me see this one, does not matter, it's gonna, this, then we move to what we call the frequency domain or the phasor domain. You also can call it the frequency domain here. Or you will hear people calling it the Fourier domain. Why is that? Because what we are doing here is nothing else but the result of a mathematical transformation that is called the Fourier transformation, if you want to talk in terms of mathematics. But at this point, you just need to remember that we are going from the circuit to the left to the circuit to the right, which we call the phasor domain for us. And from there, we just apply the traditional circuit relations, which are this one. For example, I applied here KVL, and I found this particular relationship here for that circuit. Now, what I will do next is to apply the same to this transmission line here, and then to develop the equations that you have in the previous page. And then because this page is on your website, you can look at that while I'm making the derivations here, because I would like you to see how we do things now. We have moved from a physical representation of the microstrip to a symbolic representation here, symbolic, to then a circuit representation. So this is symbolic. then to a circuit representation. And the circuit representation is the following. You have an input, and then here, where it starts as A, you still keep the two wires, but in the circuit form. They are not thick lines. You remember what I told you in the symbolic representation, the transmission line is represented by a thick line. And then here we have what we found. We have a resistance per unit length, R dz, which comes out of the ohmic losses of the conductors, and inductance per unit length L, which now I multiply with dz because this is the distance. This is the length of this line. I selected it to be a infinitesimally small length. We call it dz. And then here we have a capacitor, C dz, which represents the electric fields in this line and the storage of electric energy. And then we have a conductance, G per unit length. So I put here G dz, and that comes out of losses in the dielectric. And then here it comes out to B prime, A prime. Now, what has happened, this is the circuit representation. What happens as I move, there is something very interesting. When I go from the symbolic representation where I have a length to the circuit representation where I only have circuits. And when we go to the circuit representation, the lengths collapse. In circuit representations, when you have RLC, there are no physical lengths involved as there are in the symbolic. However, I did not lose the information about the length, dz. The information about the length is here. All right, it has already been incorporated. The only thing that I will do here is what I had above. This one is my voltage. I will still put it in red form so you see. V of Z here, because we said on a transmission line, the voltages. Now, they are not functions of time in the phasor domain, but because the transmission line has a length, and the only thing it has a length, so it's one-dimensional problem. So we went from a 3D problem where the microstrip is, with all of these transformations, to a symbolic representation where there is only 1D, the length of the line, one-dimensional. And therefore, all of the entities there will be a function of that dimension. We already have incorporated this dimension in here, in the R, in the L, in the G, and in the C. We already done that. Now we are incorporate those in the voltages and the currents. So how do we incorporate them, since in the circuit representation A and A prime and B prime have collapsed because there are no lengths involved? We are going to include it here. So at the output, we are going to write the voltage. The voltage here will be, let me just move this a little further out to the left. The voltage here will be V of Z plus dZ. Okay, so now we have incorporated the dimensions both in the elements of this equivalent circuit, on the circuit representation, or also in the voltage. And we'll do the same thing with the current. The current here is going to be at AA prime. It's going to be I of Z And here in the output is going to be I of z plus dz. A lot of times we are going to show the v at a prime as a prime, and at bb prime as bb prime. And in the currents, we are going to show this one. Move it a little higher up. Down. It's going to be a prime. And here is going to be bb prime. In a transmission line, we will always show the voltages and currents and what place on the transmission line they are. So now we are ready to write Kirchhoff's laws. All right, what are Kirchhoff's laws? First of all, we apply Kirchhoff's law here. One, that's point, say, C. This is point C prime. And then we have Kirchhoff's laws applied to C, or equivalently to this node, and to this node, which is C prime, or this one. All right, these nodes are connected. So here is what I'm writing. What do I know from Kirchhoff's laws? I know that V a prime of Z equals to R dz plus, and then here I have already, if you remember, incorporated the J omega. So there is, let me do it here. I move this here a little further to the right. And here there is a J omega here. All right, L. And for C, I have a J omega C. All right, J omega C is not a resistor or an impedance, it's an admittance. You need to remember. Like G is in admittance form, which means they have units of ohm. So, but I'm gonna come to that. So this is J omega L of Z, L dz, excuse me, here. So that's K V L. And that's multiplied by I A prime of Z, and then plus the voltage at C prime, which is VBB. All right, let me write it here. Of Z plus DZ. All right, and then what else do I have? I have that the current at C, I have the following. So KCL at point C. I have that I A prime of Z plus whatever current goes down here, which I can write it as V, write it here, V B B prime of Z plus DZ divided or multiplied, if you like, by the conductance, all right, there, which is gonna be G plus J omega C D, and all of them with DZ. So let me put it here. Sorry, I need to leave that. C G DZ plus J omega C DZ. and that is equal to I B B prime Z plus DZ. Okay? Now, I have the following. I have that V A prime of Z is nothing but V of Z practically. But I called it VAA prime to know that it is applied to this node. And I know that V prime of Z plus DZ is nothing else but VZ plus DZ. I just put the VB prime so for us to differentiate between the various places on the circuit. And then I know that I of AA prime of Z equals I of Z. And then I know that I of BB prime of Z plus DZ is nothing else but I of Z plus DZ. So now I go, this is equation 1, and this is equation 2. And what do? I go and I replace those there. And by doing that, I have the following. From 1, I have that V of Z equals R dz plus J omega L dz, and all of this multiplied by I of Z plus V of Z plus dz. And then from 2, I have I of Z equals I of Z equals minus V of Z, let me see, minus G dz plus J omega C dz, B of Z plus I Z plus dz. Okay, so this is 3 and this is 4. So from 3 now, let me give 3 and 4 different colors so you can follow them. 3 and 4. So from 3 now, I can rewrite the following. V of Z plus DZ minus V of Z, I move both to the same side, equals R plus J omega L times DZ I of Z. Okay? And then from 4, I have the same thing for I Z plus DZ minus I of Z. Now this is equal to, let me see, V minus, there should be a minus here. That is equal to G plus J omega C dz V of Z. Okay. Now, what do I do here? I will add one more page. Here, I have these two equations. I continue with the writing. Now, I divide both sides of those with dz. Okay. And since I do that, what does this one remind you? What does this remind you? Do you remember what is this? What is the, this is a definition for something that you have seen. What is it?
Yeah, it's a definition for a derivative, right? Except without the limit.
Exactly. Thank you. Thank you. So it's dv of z dz equals minus r plus j omega L I of z and di of z dz equals j plus j omega L v of z. You know, let me see whether I've made a mistake in a sign somewhere. So maybe not. Okay, so that's what you have here. I think I may have made a mistake in the sign. Let me just see. So this is I of z plus I of z. I made a mistake somewhere and nobody told me that. Look at equation 2. I made a mistake in the sign. It should be that I plus, okay, this equation 2, which is KCL, needs to have a separate sign. It needs to read, and nobody got it. That's okay, it's early. So it needs to be this here, this there with a plus, with rather this, okay, no, the other way around. Okay, let me move this back. This one is here, but there is an equal sign. This is equal plus, plus this one. Now it's better. Okay, that's the correct equation. All right, so now I have this minus, both sides have a minus. Okay, so there is a minus here, minus there, because there is a plus here, the way I have it. Okay, now we are better because there needs to be both negative signs here. So now we have this set of equations. Very important equations. You need to remember them. These are extremely important. But we're going to take one more step here. And what is the step we are going to take? We are going to take the second derivative. Let me call this equation 5. And let me call this equation 6. And now what I'm going to do, in fact, I don't need this. I will take the derivative of the first one. So from 5, then I can find the second derivative of v of z dz equals minus r plus j omega L di of z dz. And then this is 7. From 6 and 7, so from 6 plus 7, not plus, rather we don't sum up. Plus means literally. 6 plus 6 and 7, we then have that d squared. We have one second order differential equation for v equals r plus j omega L times g plus j omega c v of z. This is called that these equations that I have here are important. So this one, this set, and this one. So the first set are called the telegraphs equations. Why do we call, the telegraph? When the old days, before you were born, people did not have Wi-Fi. And if they want to send something, they would use the telegraph. You remember those from movies and stuff from the West? When people were using the Morse code and they were saying, send informations. Why is that? Because the person who found that is the person who understood how the currents that have frequency flow on a line. So how did people will send telegraphs messages through the machine? They will have a line, like a wire that runs and between two distances. And then they will have a switch and they would interrupt the current flow. And then by interrupting the current, you can use a Morse code to interrupt it. And then the current is going to be interrupted on the other side of the line. And then you can pick up the code from there. That's a simple thing that people were using. He developed that because of these equations, because he was able to understand how the current runs. And we call these equations the telegraphs equations. And then we call the result of these two equations the wave equation. And here is why we call this the wave equation. That is important for us in everything we'll do from this on. Why is that? Because this equation, do you remember this? Have you seen a second order differential equation in circuits? Do you remember that from 214?
Yes.
Good, thank you. When you have an LC in a circuit, is a second order, all right, circuit. An LC circuit, it has one very unique characteristic. What is that? What do you remember from 214?
It oscillates.
Exactly, it oscillates. Do you happen to remember what is the oscillation frequency?
I think it's square root of 1 over LC.
Exactly. So the frequency, the radial frequency is 1 over square root of LC. You're so correct. If you have any type of LC circuit, this or this, they oscillate. What does that really mean in electronics, that they oscillate?
They produce a standing wave.
Yes, but let's think it in terms of physics. With fundamental physics, what does it do when it oscillates? Here is what it does. So you remember it. This one stores what kind of energy?
Magnetic.
Exactly. And let me do it like this so you can see it. So this one here, inside here, is magnetic energy. Magnetic energy. So what is inside the other one? Here. Oops. What kind of energy have inside?
Electrical.
Electrical energy. So now we have here electric, not electrical, electric energy. that reminds me when electric and electrical are different, obviously. When, just as a break, when my daughter was very young, she's now in her mid 30s, but when she was very young, and I was explaining her, she would ask me what kind of a job I'm doing, and I would say I'm an electrical engineer. So she would go to her friends and say, my mom is an electrician. Because she did not know what an electrical engineer was. But in any case, it always reminds me those things. So it's a magnetic energy and electric energy. What happens there? The same thing applies in this one, all right? In the so over if this one, if we write it this as 2 pi f 1 over square root of LC, practically that develops a frequency from here. The frequency here is in hertz, is 1 over 2 pi square root of LC. That's the resonant frequency. So what does that mean? That frequency has a period, 2t. How much is the period for a frequency? 1 over t. You remember that? Okay, so this one over half of the period over t over 2, the magnetic energy, if say we start, if we put all of our energy into the inductor, and so we eliminate that. So over half of the time, all of the magnetic energy from the inductor will transfer to the capacitor, and it's going to turn into electric energy. And therefore, the magnetic energy from here is going to be depleted and become electric energy. And this is going to happen over t over 2. So over half of the period, that's what is going to happen. Over the other half of the period, after all of the magnetic energy has become electric, the reverse happens. All of the electric then goes back into magnetic. And over the other half period, all of the electric turns into magnetic. And that keeps forever. That's what the resonant frequency means. Over a full period, the magnetic has gone from magnetic to electric and back. So do you understand now that from physics point of view, what is happening? Is that clear? I don't hear any objectives.
Yes.
Okay, thank you. So having said that, so you keep this in mind. All right, so this is important. Now let's try to go back into this equation, equation 8. And from 8, so here, let me put a parenthesis rather. Put a parenthesis, so in case you read that, you remember that that was a parenthesis really. Okay, that's really good. So all right. So from 8 now, we have the following. We find that V of Z can have the following form. The solution to this wave equation is known to us. And the solution to this wave equation has two possibilities. So it has two possible solutions. One is what we call the V plus, and the other is what we call the V minus. And I will explain those. V plus is V naught e to the minus j beta z, and V minus is I naught, and here we also put a plus here and a minus there, of e to the j beta z. Okay, what does that mean? One more page. Not there. Delete. Okay. These are very fundamental solutions and are extremely important. So let's go back to see those solutions. We'll go back to the symbolic form of representation of the line. So this is one line here, and I feed the line has here one input port A. A prime, and an output port B prime. And this is the symbolic representation. So I put it here so you remember it, symbolic. Now, when I excite it here with the voltage V, all right, let's assume that this is Z equals 0, excuse me, Z axis. At this point, let's assume that the axis equals B equals 0. And let's assume that at point A prime, we place a voltage V at A prime equals V naught. So we fix the value for this voltage. And let's assume that this is Z equals L. All right, as a matter of fact, you will see that eventually we are gonna move Z equals 0 to the end of the line. And as a matter of fact, I will do this first because it's easier for you to see it. And then I will do the other one. So you may ask, why do you put a Z equals 0 now at the source? Because that's what we are used doing, all right? We always start at the source. But then you will see that we are gonna move the Z equals 0 to the end of the line because we are gonna always be interested what happens at the end of the line, which we call the load. So this is the source side, and this is the load side. I'm giving you now some names, so you have to remember those names. We'll use them quite often, so you're gonna get used to them. So what this solution tells us, which is extremely important, it tells us that this voltage has two components. One is a voltage that we normally show like this. It's a wave. Both of them are waves. This one, we call it the positive Z wave, and it's the one that has the negative expression in the exponent, the negative, which is V naught plus, we always put a plus to remember, e to the minus j beta Z, and I will explain what it is. And then it has a possible solution also that looks like this. Oops. And then we call that the reflected wave. So we call also, I will put here the name. So this is incident wave. Remember the name. And now the other solution, it's V minus of Z, which is V naught minus e to the j beta Z. And that's called the reflected wave, and goes like this. Now, one thing that you need to remember, in addition, even if I show one on top, one on the bottom, I do that because I don't have space. But in reality, both waves go inside. These are voltage waves. So what do they represent? Electric field. Where is the electric field only? The electric field applies only here. Remember, the electric field, which is this, applies here. So practically those waves are waves that are inside the line. So they go, the wave V plus, it's a voltage wave, it applies between this and that, but it's a voltage that goes like this, V plus. And V minus is also a voltage wave. It applies like this, but it moves like that, V minus. All right, these are the two solutions. There are two waves. So the incident wave, incident, and always we show it like this. It has a magnitude and it has an exponential. We'll call it phase. Whatever is the exponent, we call it phase. And the reflected wave, which is V naught minus, and that's V minus, which is V naught minus e to the j beta z, where now beta from this wave equation, where beta is nothing else but the square root. And as a matter of fact, instead of beta, what I will use a different, we'll call it gamma. I don't know what the book is using. Let me see for a second. It uses what the book is using to make sure that I'm using the same. 1 second. I don't want to change. Formula the book is using. Parameters. Gamma. Okay. All right, let's use gamma here. So the same thing, I will call it, it's okay to call it like this, but the book also uses the following relationship that you are gonna also see, called the book uses, I'm gonna put it here. So J beta, where J beta, and the book uses that gamma, is nothing else but R, oops, R plus J omega L times G plus J omega C. All right, so also you can, in the most general case, therefore gamma and beta are complex numbers. The book, the way I have it here is like that, but you can rewrite these waves, all right, as in the most general case where there are losses, and I will show you why I write it like that. Gamma is equal to alpha, in general is a complex number, J beta, and also minus gamma, therefore it's going to be minus A minus J beta, where in the general case of losses, in the general case of losses, then alpha and beta are different than 0, and they are positive numbers, real numbers, so positive. Let me write it rather, sorry. In general, positive, real numbers. All right, so in the case of lossless lines, and most of the time we're going to look at lossless lines, gamma becomes J beta. And therefore alpha is 0. So beta in this case is nothing else but omega square root of LC, which is also very interesting. All right. So look at this one here. So practically what you have in there in the circuit is an expression of the resonant frequency as well for this small section of line. Okay, one more thing that I wanted to say, let me do this one here. Now that we have defined those, let's see how the voltages will look like. So practically you have V of Z will be, in general, V of Z plus V of Z minus. This is the general expression, general solution of V of Z. And we are going to use those starting next time. We're going to start solving problems then, because we theoretically, this is all the theory that you're going to see from transmission lines. So here, and then I of Z, so I'm going to write everything here, is going to be I plus of Z plus I minus of Z. And that's the general solution of I of Z. So now what do we have? In the lossy case, losses, therefore, we have that V of Z has the form V naught plus e to the minus AZ e to the minus j beta Z plus V naught minus e to the minus AZ e to the j beta Z. And as a matter of fact, in this case, assuming that it goes along the negative Z direction, all right? So this, remember, this goes like this along the positive Z. And this wave here underneath it, this is the opposite wave. It goes along, this one goes along the negative Z direction. You need to remember that. That's why there is a plus sign in front of A. In the case, and a plus sign in front of B and Z. In cases of lossless, which we are gonna do, we are gonna start with lossless. So that's very important to remember, because ideally we don't wanna have losses in lines. I mean, the reason we eventually include losses is just to predict what is gonna happen if we have losses. If we were, the ideal line would be without losses. Otherwise, who wants to lose power in any line when you transition power from one to another place? Okay, so in a lossless case, we're gonna have, now I'm writing everything. V of Z is gonna be V naught plus e to the minus j beta Z plus V naught minus e to the j beta Z. All right, so this is one. And for the current, we have I of Z, I naught plus e to the minus j beta z plus I naught minus e to the plus j beta z. And now what is the relationship between I naught plus and I naught minus? Where V naught plus over I naught plus is a new entity we call the characteristic impedance of the line of the line. And we show that equal to Z naught, and beta is the propagation constant for the line. Where now I know both of those from L and C. Z naught is the square root of L over C, and beta is omega square root of LC. All right? So this is exactly what we need to know. From all of these, the only things that we will remember for now are these two. And of course, the relationships between I naught and V naught and beta. And that is going to give us everything we need to know to start writing problems, doing examples, starting on Monday. Do you have any questions so far? What I would suggest, because on Monday we're going to start with problems, and I will start some problems this evening also with a problem solving session, if you want to join. But definitely on Monday, I will repeat those for those who are not here this evening. What I wanted to tell you is please read this material so you become familiar with the definitions, because I'm going to use them from this point on. I'm not going to go through these equations again. I will assume we know all of this, and I would like you to remember by heart this. This I expect you to remember by heart, because if you don't, and if you have every time to go and find this, you're not going to be able to solve problems easily. All right, so we don't expect to know too many things. By heart, we expect to know in a class like this the definitions and the physics around them by heart. But I want you to remember this. And I want you to remember that these are incident waves and these are reflected. Incident, reflected. We call them incident because they move from the source to the load, and we call them reflected because they are reflected by the load back to the source. Okay? So this is what I want you to read. I'm gonna put it on the website, so you have access to it over the weekend, please. And then we don't have a class on Friday. As a matter of fact, you remember this is a reading day, and there is no like on Thursday, there is no redefine. We did that last time. So you have time to go through this. Please focus also on your homework. I will give you new homework on transmission lines on this on Sunday. Will be a simplistic homework to just warm you up. And then we are going to solve problems from now on transmission lines, because that's all to it. I mean, this is the only theory you need to have and nothing else. And the rest will be problems, and we will see what we are going to do, because everything you need to know to do on a transmission line is to reduce its reflection or to make the reflection something very specific. I will talk about that, and I will give you some examples of where this happens and why. It's very broad. I mean, it interconnects. If you want to design a circuit, that's all you do. All you need to know. This is like the Bible for people. This is like the alphabet for all of us. This is like the 1 to 10, knowing the numbers. That's how you need to know this stuff. And then from there, it's just solutions and experience that you get. All right. Any other questions, please? I hear none. So enjoy the rest of the week. And either I will see you this evening or on Monday. Thank you.